Our next topic in our chapter on heat energy deals with enthalpy. Enthalpy of a system is denoted with a capital H. I often think of H as being the heat of a reaction. Enthalpy of a system is the sum of the internal energy of the system and the product of the pressure and the volume. In other words, when chemistry actually is happening, not just heat flow from a hot object to a cold object, but when we actually have bonds breaking and new bonds forming, when the system is the actual chemical change we are studying, the correct term for that type of energy is called enthalpy, and it gets denoted as an H, a capital H for the term enthalpy. We can see that endo and exothermic reactions denote with a negative sign for exothermic when the change in enthalpy, heat being released by the system, will be termed exothermic and gets a sign showing negative. Heat is being lost by the system to the surroundings. Reactions where delta H is positive shows an endothermic reaction. The system is gaining heat energy from the surroundings. And this is simply showing a chemical heat pack and a chemical cold pack. A cold pack representing an endothermic process where ammonium nitrate dissolves in water. Endothermic process, your hands would actually get cold holding on to this chemical change. If heat is being released to the surroundings from the system, we call that an exothermic, and your hand would actually get warm to the touch. Endo is heat absorbing from the surroundings. Exo is heat releasing to the surroundings. Endo is a positive sign. Exo is a negative sign. Taking a closer look at a molecular view of exothermic reactions. For exothermic, the surrounding temperature rises due to the release of thermal energy by the reaction. This extra thermal energy comes from the conversion of some of the chemical potential energy in the reactants into kinetic energy in the form of heat. So during the course of our reaction, old bonds are broken and new bonds are made. If the products of the reaction have less chemical potential energy than the reactants, that difference of energy is then released as heat. Again, as reactants turn to products, if heat is released, the energy of the products was at a lower state. The enthalpy of reaction is a chemical reaction is an extensive property. In other words, the more reactants you use, the larger the enthalpy change. So by convention, we calculate the enthalpy change for the number of moles of reactants in a reaction. And let's just take a look at what this could be interpreted as with this example. C3H8 is a molecule known as propane. We often use propane in our gas grills at home, or some people actually heat their homes with propane. When it combusts, it reacts with oxygen from the air, forming carbon dioxide gas and water vapor. When propane combusts with oxygen, it releases carbon dioxide and water. The delta H, the enthalpy of reaction, is negative 2044 kilojoules of energy. The negative sign shows exothermic. We just said we use propane as a fuel to either cook our food or heat our homes. We can see that there's energy being released that we trap as thermal energy. To read this, see the coefficient in front of the propane molecule as a 1. For every 1 propane molecule that combusts, 2,044 kilojoules of heat is released. Or, for every 5 moles of oxygen that combust, 2,044 kilojoules of heat is released. What we're reminding ourselves is that delta H is just like any other part of the balanced equation and can be placed into any stoichiometric ratio with want over given, grabbing kilojoules per mole. And let's model what one of those would look like. In example 6.7, how much heat is evolved in the complete combustion of propane? And the mass that they're giving us is 13.2 kilograms. 13.2 kilograms of propane. Well, Just as a side note, this kilogram should be placed into a gram unit as entering into our stoichiometry roadmap. I remember that 1,000 grams is equivalent to 1 kilogram, that prefix kilo stands for 1,000. So if we simply multiply 13.2 by 1,000, we'll just slide the decimal place. I can show that, but you can probably do that as mental math. Sliding the decimal to get rid of the kilo gives us 13,200 grams. And that's where we'll begin this journey. 13,200 grams of propane, C3H8. This is what we call our given, and we want to know kilojoules, kJs of heat. We know that coefficients stand for mole numbers, not mass values, so we need to do a little mole map work. We need to look up a molar mass of our molecule propane and use that to convert into the mole. Carbon with a weight of 12, and I see 3 of them in the formula, so 12 times 3, plus hydrogen, who has a weight of 1, but there's 8 of them all together in our formula. The molar mass of propane molecule is 44. That tells us that every 1 mole of our propane, C3H8, would weigh 44 grams. The gram units cancel and it brings us into the mole. We're now ready to do the heart of our problem, the stoichiometric ratio of want over given. We want to know kilojoules of heat energy. There's 2,044 kJs of heat released for every 1 mole of propane that combusts. A want over given ratio of 2044 set over 1. We've canceled the grams, we've canceled the mole unit, and we're left with our target, the kilojoules of heat. And let's hit that together and see if we get a common answer. Starting with 13,200 grams, divide by 44, and multiply by negative 2044, and we find a value 613,200, and the negative sign lets you know, we know it's exothermic. So 613,200 kilojoules. Again, we used a mole conversion and then a stoichiometric ratio, want over given, where we targeted kilojoules from the mole of reactant propane. Our next practice, very similar. How much heat is evolved when 0.438 grams of diamond is burned? Well, diamond